Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about parsing expressions. This is pretty much the last thing that we're going to have to do before we start actually getting into the backend side of the compiler. So this one's going to be pretty interesting. The way I'm going to actually do it is here. I'm going to go to this file syntax. In expressions, like expressions are used pretty much almost everywhere in the parser. It's kind of splattered around. So I'm pretty much just going to use parse variable declarations. This is typically what I do when I've been like testing it. I would basically call the function parse expression in here, and then I can easily just print out the value. That way I don't have to like do any crazy syntactical things. So here I'm going to create a simple class called foo, and we're going to create a field called foo field. And we can assign it a value. So let's kind of see what we're going to be processing first. So the first thing we're going to do is for expressions, you want to start off by creating your AST underscore expressions. Now this is a pretty complex function. This has tons of different things. We're going to have to split this across multiple videos, but I'll try to get this done as quickly as possible because I really do want us to get to the backend side of our compiler. That's actually where the fun is. So after you create your parse expression function, which you guys have already should have done, after you create your AST expression, you want to check your error limit. This is very important, guys. Like, as I mentioned in a previous episode, expressions are going to be recursive. Now, I got a comment mentioning that why not I do like a flat version of parsing expressions, and I do a mix of both. But yeah, you guys will see that in a little bit. So just make sure you check your error limit here because we could, like, if you break something in your compiler while you're testing or whatever, you don't want to generate thousands of errors. So the first thing we're going to want to do is we're going to need to pre-increment our expression. So here I created a quick example here for you guys. So like let's say we have a health value and we want to, for whatever reason, plus the health. Now you can ignore the fact that this is called foo field. That's not really the point of this example. The point of this example is just to show that we need to plus a value. So because I haven't shown you guys everything for parsing expressions yet, the only thing I'll be able to show you today is using a actual value. So like, now ordinarily you wouldn't do this in the compiler, but let's kind of just see how we do it. So when you're plussing a value or an expression, you just check for increment or decrement, which is these two values, and you create a pre-increment expression. That's what the AST pre-increment E is. So you create that branch as the expression AST. You add the value, whether it's plus or minus, to this AST, and then you parse the expression. Now, please note, use this, don't use branch, because this is a child or a subset of this branch. So that's very important. But yeah, so you literally just call back into this in whatever parse expression processes, you will plus or minus it. Now, obviously, if you do some dumb stuff on the back end, we will cover for that, but this one's a pretty easy one. So after that, you want to basically start parsing your primary expressions. So if we go here to grammars, here I'm going to go up here to grammar sheet, and we look down here. Now this is very important. I'm going to be referring to this occasionally throughout the series while we finish up the parser. But basically you can see down here we have a grammar for an AST expression. The first thing you need in an expression is a primary expression. Now what is a primary expression? Primary expressions are basically the main types of information that you're most likely to process, and you should probably order it in terms of like likelihood, right? I tried my best to order in terms of likelihood because you don't want your parser to be churning too hard. So this is kind of the purpose of primary expression. And it's also to allow you to individually process single things. Because when you get down to parsing these, it's a bit more arbitrary. Like you can see here, right, we have a plus, minus, some expression. We have a not, some expression. So like if you say not some function, or like you have like a vector array, which is basically just an anonymous array, or you have like, you know, math expressions, right? Well, the only way you can process an expression, you know, times some other expression is you need to have a primary expression which represents all the things that you can process that are single value expressions. Basically, they evaluate to or resolve to a single value. So hopefully that made sense. Probably did a bad job at explaining that, but let's kind of see how we do it. So first you want to keep track of your old token, because if you try to parse a primary expression and you fail, then you want to reset the uh, current token. So before we go into creating this function, just make sure that we have the necessary code on the outside first. So primary expression is going to be a function that returns a Boolean. So make sure you create that, and it obviously you pass it an AST. Now, after we parse a primary expression, you want to check something, and this is very important. So this is kind of how we get the functionality to do like expression, like this, for example, expression plus expression. So what you want to do is you want to check for an expression symbol. Whoops, let me go back. So you want to check to see if the next character is an expression symbol, and this is immediately after you parse a primary expression. Um, and that entails basically any one of these values. So I'll let you guys copy this function down. I'm not going to go through it, but you can see here that we basically support an array of different characters, and these are all dependent upon, if we look in our grammar sheet here, these are all dependent on basically these little in-between values, or these in-between tokens here. So we want to be able to process that information, and you can even see here I also have a expression, a sign expression, and another expression. So that is this. So is a sign expression symbol. So I'm going to go here really quick, pause the video if you guys need to copy down these expressions. So when we go to a sign expression symbol, what these are these are symbols that are pertaining to specifically assigning a value. Now, it's very important that you split out these two functions. You don't want to have like just a giant is expression symbol function, because we're going to be using this is assign expression symbol in other places in our parser. So just keep that in mind. So let's go back. So now once after we parse our primary expression, if we find, for instance, I don't know, let's say we find this question mark, right? So let's say we have some Boolean here, right? So let's say we had an expression of is player dead, right? And it's a function. We had a question mark. Well, that would allow us to then parse, and we'll go over this in a little bit, but that will allow us to basically parse a inline if statement. So you guys have seen this before in programming languages where you have an expression, a question mark, and if the expression is evaluated to true, return this expression, otherwise return this expression. So that's kind of the concept behind that. So like that's why we need to have this is expression symbol. Take that back and go back up to the top. So once we've decided, like, so if it ends up not being an expression symbol, then we just want to return true, because that means we successfully parsed our expression. And otherwise, if we just completely failed and it's not even a primary expression at all, then what we want to do is we want to reset the current token to the previous value. Okay, so I just changed some code here. So after you do that, then you want to basically free up the last sub AST. So let's kind of jump into parse primary expression to see what we can do. So first you want to create an AST of primary expression. And the first primary expression we're going to process is a literal. This is going to be the first most likely outcome or most likely expression that the user is going to be processing. Users usually type in literal values all the time, like numbers, strings, booleans. So let's kind of see how we process those. So the first thing you want to do is you want to enter protected mode. Now this is where we get into complex error reporting. If you guys remember a while back, I created this function called enter protected mode. And you guys can review the code here if you guys would like. It's in the error manager. And I think I mentioned this before, but basically all it does is puts the error management system into a protected mode. So it effectively adds an error list to the actual error management system, and it basically acts as a temporary buffer, so that way you can throw errors at it as many times as you want. So like if you, for instance, generate 5 errors, those errors are not going to be directly reported to the user yet, because they're not determined to be real errors yet. So you want to use this possible errors list as a way to not tell the user that they messed something up, because as you know, there's thousands of different situations that you can have different various forms of expressions, and you just want to make sure you complain to the user in the correct way. So first thing we want to do is enter protected mode. After that, we want to set our current token. We want to save our current token. So that way, of course, if it's not a literal, then we can just go back to where we were. So before we get into parsing a literal, if it's not a literal, like if that's not true, then you want to free up the last sub AST because of course parse literal is going to create another branch. Then you want to call errors.pass, and what that does is that effectively deletes the last possible error list. So that will check the protected errors size, and if so, it will get the last one and clear up the errors and then just delete it off the list. So that's kind of how that works. And then of course you want to reset your current token to what the old value was. Before we also get into here, this kind of is dependent on stuff in here, but I'll mention it briefly to kind of explain what's going on. But for now, all you need to do is if you successfully parse the literal, fail the errors, right? So if if there was maybe a malformed number or I don't know, whatever, if there's any errors in parsing a literal, then of course you want to report those. Then you want to encapsulate this branch into a literal E. So what encapsulate does is, I think I mentioned this before, but encapsulation, the concept of encapsulation is here. Let me go to paint. So here, the concept of encapsulation is this. I'm going to start to draw. So like, let's imagine we have here our parser, right? Or our primary expression. So this is going to be this is going to be our primary expression. Okay, you guys get the point. I'm not even going to try to write it. And our primary expression contains, a literal value of 1. So this is going to be our AST literal. Now, in order to successfully pretty much denote what type of AST this is, you want to encapsulate the values. So in order to encapsulate the values, you basically want to look at this AST here, and you want to basically create another AST called AST underscore literal E, and then you want to steal all of these sub ASTs from this AST. So you say, all right, put all of those sub ASTs into this one and then destroy them in here, meaning that you basically lose the references to those values. And then what you end up doing is you say, all right, well, I'm going to put this AST now back into here. So now, whereas our primary expression had one AST of AST literal, it now has a new AST with that one encapsulated inside of it. So you effectively do this. You have this AST and then this one. Now this example is a bit strange when you only have one AST, but imagine if you had like 3 ASTs inside of this primary expression. Well, all 3 of those ASTs would go into here, and then you would effectively have one AST that contains all of the information that you need, and then you can process the data accordingly. So that's why encapsulation is pretty powerful. So that's kind of how it does it. So next, after that, let's kind of look to see how we parse a literal. Oh wow, so I actually thought this would have been a lot more in depth. Okay, I guess not. So when you parse a literal, first thing you want to do is create an AST literal, and you want to peek the next token, and you want to just check to see if it's any one of these values. Whoops. So if it's a char literal, integer literal, string literal, hex, or true or false, then you want to add that token to this AST, and that's it. And of course, you want to return true because this does need to return a Boolean. Otherwise, you return false. And now this is where you get into the errors. Now, if we were parsing a literal in a different sense, like maybe in a different AST, and it needed to require a literal for its formatting, then of course this error would be printed out. But in this case, for parsing an expression, the literal value will not be printed out because it is simply passed. So we just ignore that error. So yeah, that's pretty much all you need to know about parsing literals. Now, once you successfully parse a literal, like I said, I was going to briefly mention this. What this basically is, this code, basically you need to have like other values after you parse an expression. So here, I'll give a better example. Let's see if I can find one. So like, let's say we have something like this, right? So this is called a self expression, and this is basically like the this in Java, but except in my language, it's self. So let's create our health variable again, of int, and let's say we wanted to access that. So this is a bit redundant, but you can say self dot health. And what that'll do is that'll get the health variable from this class. Now, if you had like a base class of some value or some class, and that also had a health variable, well, then you would get this variable from this class instead of the base class. But if we look here, you can also process other things after this. So this is where we get into basically flatlining the processing of primary expressions and not using recursion. So what you do is you check to see if you have a self. You basically parse what's called a dot notation call expression, and we'll get into that later. And you encapsulate that value. And then after that, you want to check to see if you have other things behind it. So like, let's say, this health variable is an int, right? Well, that means that we can do this, self plus plus. Or we can also do something like self minus minus. Now, this would get processed in a different way. This would get processed at the higher level before we even get to parsing our expression. If you guys remember, before we get to parsing our primary expression at the high level, we would process this first and then primary expression. So this is actually backwards. This should be actually above this. Or let's say we have another example. I don't know. Let's say we have like a left brace, right? So let's say health was a value or like an array. So instead of maybe health, let's say we had like a body parts. I know this is a shitty example, but bear with me. So let's say we have like a body parts and we want to access the 0th index and we want to plus plus that value. Same thing, right? Like if you want to do that for self, well, how the hell do you do that unless you check to see if the next character is a left brace and then you parse an array expression. So that's kind of the point of this. But I guess you guys can probably write this down. So for literal expressions, what you want to do is you want to check to see if there's an increment or decrement. And then you want to basically get the last sub AST. Now, this is kind of unnecessary, especially considering I just encapsulated this. So here I'm going to say branch.get last sub AST. So what you want to do is you want to now edit this branch value because if you remember, we encapsulated the expression AST into branch. And if we didn't do that and we went down to basically checking our increment, like so whether or not you have an increment or decrement after the expression, if we went down here and then we created this AST post increment branch, what you'll effectively do is you'll have two ASTs inside of primary expression. And that's bad. You don't want that. You only want one, you only ever want one AST residing inside of primary expression. So that way, when you process it, you know what you're processing. Because if you think about it, it makes sense. When you go into the back end here, I'll show you guys an example. So I'm going to go to my compiler and I'm going to do a search for compile expression. So if you guys see here, when I'm parsing a primary expression, I literally have just like a switch statement, which basically processes everything. And when we go into here, you can see I have all of my various different expressions. So I have literal, I have lambdas, and everything else. And you can see that I pretty much just get the first sub AST at index of 0. And I'm expecting that whatever the hell the formatting is, it needs to be that formatting. So in the example where we had like the self, body parts at 0 plus plus, what that would end up being is that would be a AST post increment, and if we go into here, we would basically parse the expression of self body parts at this. So what this would be is this would be an array expression, and then when we parse our array expression, then we would basically process self body parts at 0. So you can see it kind of goes down backwards when we're processing it. I don't want to confuse you guys too much because we'll get into the mechanics of that later. But yeah, just keep that in mind. There's a lot of gotchas when it comes to parsing expressions. So I would recommend if you guys were building your language in other parts of the series, you guys can kind of like do your own thing. But I would highly recommend you just kind of follow me almost to the book on this one because there's, like I said, there's a lot of gotchas and there's tons of bugs that you think it might be okay to just not do this, but like it'll bite you in the ass later. Anyway, after that, you want to check for other things. So if you have something like a dot, so if we go back to our example of 10, if you have like a dot and then get value is actually a function a byproduct function of the int class, but I mean, this is a number, this is a literal, so it's not a class, so that doesn't make any sense. So you just want to complain about that. If you get a left brace, complain about that. And if you get an as, this is basically the way we cast. So like you can say 10 as int. And in my language, you can basically cast a literal into a class, but you have to explicitly say that I want this integer, or this literal, to be casted into this int class. So that's why you want to have that. You can just probably have nothing. So like for right now, you can just do that. Or you can comment out the code until we add the as expression label later on. But yeah. All right, so now let's kind of see how the code actually looks. So I'm going to go back to parse variable declaration, and I'm going to put a breakpoint at the code here. So let's actually see how this looks. All right, so here we are. So now let's kind of look to see what our expression code generated. So we can see here we have our AST expression for our number 10, and it's a primary expression of a literal, AST literal of number 10. So now let's also look at the other case where we have a plus plus 10, and that's going to be the code. If you guys remember when we were parsing our expression, the first code that we saw when we first came in. So let's see how that one looks. And this will kind of show you guys how encapsulation works. So if we go back up to here to our AST expression, so we can see here we have a AST expression, and instead of having a primary expression next, we have a AST pre-increment, which we have our plus plus here, which denotes that we want to increment our value. And then we have one AST of an expression, primary expression of a literal of number 10. So that's kind of how that works. And of course, just to be complete, you can also do a minus minus as well. And we can also see that the minus minus will look just the same. So yep, we have the same formatting here, pre-increment, minus minus, with our expression of our literal of 10. So that's going to be it for today, guys. This is parsing literal. I know I explained probably a little bit more than I needed to, but I want to get like the prerequisite information out of the way because as you've seen before, that graph is going to start speeding up. So hopefully everything made sense today. As usual, if you guys have any questions, definitely write them in the comment section below, and I'll get to them as soon as I can. Also, as per usual, if you guys would love to help support the channel, definitely head over to my GitHub repository at androidevcd/sharp. And when you guys get there, definitely watch, star, and fork this repository. That's going to give this language a lot more visibility and lets other developers know this language exists. Also, if you guys are interested in kind of seeing the day-to-day on what I'm doing with the language, maybe updates I've made to it in the past couple of weeks, you guys can head over to the remastered branch. And in there I write some pretty wordy commits. As you guys can see, you can pretty much get a gist of what are some of the things I've been working on in each commit without really having to look at the code. Also, if you're interested in maybe seeing stuff that I've added in the past to the language in terms of like updates or maybe stuff that I'm looking to add into the future, definitely head over to the docs folder. And in there, you have two main files. You have your change list file, which is going to be pretty much everything that I've done in the past to the language in terms of updates, bug fixes, so on and so forth. And then you have the roadmap file, which is going to contain pretty much everything that I've done to the language thus far, as well as things that I'm looking to add to the future. But yeah, so hopefully you guys enjoyed the video. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. Until next time, I'll see you guys later.